Hey everybody! Welcome to Proofs by Contraposition with me. So far we've only used direct proofs. We've done P implies Q, or for all X, we get P of X implies Q of X, but that's not always going to be enough to get the job done. So while direct proof is ideal, it's not always possible, and so that brings us to indirect proofs. It's where we utilize logical equivalence in order to help us. So I'm going to take you back. Remember, we talked about contrapositive, inverse, and converse? Specifically, remember contrapositive, I proved that P implies Q is the same thing as not Q implies not P. So not Q implies not P is the contrapositive statement, and it is logically equivalent to just P implies Q. We can use this to our advantage to come up with easier things to prove. So if I were to give you steps, first step, state that you're doing a proof by contraposition. That way I know what's going on. And then since we're doing contraposition, now we're going to have this statement to prove. So that means you would say, suppose not Q is true, which is step 2. And then using basically a direct proof, you're going to get from not Q to not P, and then you will be able to conclude that P implies Q was true, because it is logically equivalent to the contrapositive, which you just proved is true. Okay, let's go ahead and see this in action. Let's start with example 1. So we've got some integers, and we want to prove that if their sum is odd, then at least one of those integers is odd. I'm not going to just jump into a contrapositive proof. I am going to try a direct proof. Direct proofs are preferable. So if possible, do a direct proof. You should use contrapositive as like a secondary tool. Be like, oh, well, I couldn't get anywhere with this, so let's try a different method. Okay. So let's see what happens. We say x plus y plus z is odd, and then we can apply the definition of odd. X plus y plus z would be equal to 2k plus 1. And then it said something about at least 1, so maybe I'll solve for one of them. And now it's just like, okay, well, x is definitely an integer still, but now what? Like, I need more information about y and z in order to come up with a conclusion for x. Like, I could try and do cases, but then I would be like, oh, y is odd and z is even. Now I'm kind of like concluding or using the conclusion in my proof. And that's bad form. We know we don't want to do that. So what does come next? This is a wall that tells us maybe we shouldn't be doing a direct proof. So let's think about the contraposition. So what's our P of X? It's x plus y plus z is odd. So then not P would be x plus y plus z is even. And then Q was at least one of x, y, or z is odd, which is the same thing as or. Remember, or says I just need one of these to be true in order to work. So x or y, oh, that's not an or. That's an or z is odd. So then not Q is going to look like x and y and z are even. Remember, when we apply the not or the negation, it turns ors into ands. And then the opposite of odd would be even. So there we go. That means we have not Q implies P ready to go. So we need x, y, and z to be even, implies x plus y plus z is even. So here's our logically equivalent contrapositive statement that we're going to prove. We know how to do this. We've played this game before. We just have to find the right k-bar. So let's go ahead and start the search. So we're going to say suppose x, y, and z are even. That means there exists a j, k, and an l that are integers, such that we can write x equals 2k, y equals 2, or let's use them in the right order, 2j, 2k, and z would equal 2l, like that. So then if we look at the sum, we have 2j plus 2k plus 2l, and we can say that j, k, and l are all integers. And then, I'm gonna get rid of this. I'm just gonna chase the equivalence and say j plus k plus l. So now I factored out a 2, which means I have found my k-bar. So k-bar is gonna be j plus k plus l, and it is an integer. There we go. We can say that x plus y plus z is even by definition of even. There we go. So that's one proof. Let's introduce new math toys so that we can have more math fun. Specifically, we're going to talk about greatest common divisor. You see this? This says GCD. You're going to want to say greatest common denominator. Don't. It's greatest common divisor. So the greatest common divisor of A and B is the largest number that divides both A and divides A and divides B. So pretty straightforward definition. It divides, it's the greatest one. And we denote it using GCD of AB is equal to K. For example, let's take this for a quick run. The GCD of 4 and 8, that's going to be 4. The GCD of 12 and 30 is going to be 6. And the GCD of 5 and 22 is going to be 1, because 5 is a prime number and 5 does not divide 22. So biggest number that we're going to get to go into both of them is going to be 1. Let's take this example for a spin as well. So suppose we have two integers, a and b, and we say that a is bigger than 1 and b is not equal to 0. If the GCD of a and b is 1, then we say a does not divide b, which makes sense. And we're just like, okay, so in the example we just had, we had 5 and 22, GCD was 1. So, and 5 definitely did not divide 22. I can buy this. But how do we prove that? Let's try and go at it directly, because we are good mathematicians and we try and do direct proofs. But we're going to, so when we start with, suppose the GCD of AB is equal to 1, that means there exists, not exists. That means every integer that isn't 1, so for all k in z, such that k is not 1, we can't have k dividing a and k dividing b. So either it doesn't divide a or it doesn't divide b. Why is this? Oh, and I want to go ahead and restrict it to the positive. So positive numbers. Why can't it divide one or the other? Because if it divided both of them, then we would be able to say that the GCD was equal to k, because you have found a number bigger than 1 that divides A and divides B. So here we go. We can chase it maybe a little bit further. We could say that A maybe equals, we'll say KQ plus R, say Q1 plus R1, and R1 doesn't equal 0, or B equals K times Q2 plus R2, and R2 doesn't equal 0. You're like, okay, so I said that I can't divide it, so I can't have, if we didn't write that, we could write A doesn't equal that, or we could admit that there's a remainder. But either way, like, what do you do at this point? If there was an and, when you have this equals blah and this equals blah, you can start doing things like substitutions and stuff, but we have an or. So what do we do at this point? We're kind of stuck. Like, you could try doing cases, but what cases would be helpful? Yeah. So that's when we abandon this and say, we tried our best, trying to do something else. So contrapositive. So what are the P and Q statements first? If P, then Q. So now let's write our contrapositive statement. So if not Q, so that would be A does divide B, then let's see, not P, so that means GCD was supposed to equal 1, so we're going to say that means the GCD doesn't equal 1. All right, let's try and prove this. So proof, suppose A divides B. Well, we know A divides itself, and that's what GCD is all about, things that divide A and divide B. So let's talk about A divides itself. We know A divides itself because we can write A equals A times an integer, specifically 1. So that means we have A divides B and A divides A. So that means the GCD of A and B is greater than or equal to A, because it's the biggest number that divides both of them. And so since we know A is a good candidate, then it could be A, but it might be bigger. And so then we think about it, like, can we restrict it to being not bigger than A? Like, yeah, if you've got a number bigger than A, it's not going to divide A. So let's go ahead and acknowledge that. Any number larger than A doesn't divide A. Okay. So then GCD has got to be equal to exactly A, but A was bigger than 1. And so A does not equal 1, which means we are done. We should take a moment and be like, okay, so that means if the GCD is 1, A doesn't divide B. Take a moment and reflect on what we were originally trying to prove, but we don't have to like go back and rewrite that original statement. Okay. As long as we prove that statement and we say that we're doing proof by contraposition, we are good now. Next thing that I want to talk about. We're kind of going to revisit an old friend now. We've already talked about rationals, but we're going to talk about them a little bit more. Remember, a rational number just looks like an integer over another integer, where Q is not 0. And we can say that this is in its lowest terms if the GCD is equal to 1. So if the GCD were not 1, that means that you could have like, oh, 2 divides P and 2 divides Q, and then you would have cancellation between top and bottom. And if we can't write x in terms of integer over integer, we say that it is irrational, which makes sense. If it's not rational, it's irrational. So let's compare the difficulty of proving x is rational and x is irrational. So if x is rational, we would need to find 2 integers so that x would equal integer over integer. Not so bad. Finding 2 integers can be, that's okay. We can probably do that. We're very good at finding integers. That's what all these prove it's even, prove it's divisible by. It's that game. Now, if it's irrational, we have to show that x does not equal p over q for absolutely all choices of p and q. And not only that, we have to do all the combinations. That's a lot of stuff to go after. That's a lot more than 2. So that's why when we're trying to prove irrational, as soon as you see, oh, I need to prove irrational, oh, I probably don't want to do that. I need to like get some sort of contraposition going so that I don't have to deal with irrationals and I can just keep playing with rationals because rationals are nice. For example, let's say we have x is a rational number. That's what the Q notation is. If y is irrational, then the sum is going to be irrational. So a rational number plus an irrational number is always going to be irrational. How do we know that? Well, we're going to be good. We're going to try and do a direct proof. We're going to say that x equals p over q and y isn't. What we need to do, so need to prove, or I think I always use want to show. Want to show x plus y does not equal some other rational number, like a over b. For any combination. Okay, I wrote it down. I don't know what to do anymore. So I'm going to get rid of it and say, I tried! Quick! Stop trying to prove things are irrational. Let's look at the contrapositive statement. So let's find P and Q. We say y is irrational. So if P, then Q. All right, so if not Q. So x plus y is irrational. If we negate that, that's going to be x plus y is rational. Thank goodness. Then not P. So not P would be y is rational. And then this is essentially the domain. We leave him alone. Domains don't get changed. All right. We can deal with doing rationals. That's better. Proof. Suppose x plus y is rational. Then, maybe I should use a different, we'll do capital P and capital Q. That way I can say x, plus y is equal to P over Q. And don't forget, X was also rational. So let's put that in there too. X. So X and X plus Y are rational. And then these are all going to be integers. And we know that the denominators are not 0. Okay? You should probably already see where this is going. We can plug that X into our the X plus Y, like that. And you're like, oh, P over Q minus A over B. Yeah, that's going to be a rational number for sure. But we are going to be careful. Okay. And then let's keep track of our information. A, B, P, Q are integers. B, Q don't equal 0. And I don't want it to crash. There we go. And we can say that PB minus AQ is an integer. And so is BQ. And we know BQ doesn't equal 0 because not 0 times not 0 is not 0. So that means that Y is a rational number. That is exactly where we wanted to get, because that is the Q for our, that's our not P for our contrapositive statement. Thus, the original statement is also true. All right, so that's all we have. We talked about direct proofs are superior. We like them. Why do we like them? I'm gonna go on a small rant. We like them because if you do a direct proof, you kind of like know more information about the system that you're working with. Whereas like here, we used rational numbers because we don't really know things about irrational. It's just like, oh, it's irrational. It's not rational. Crickets. And so that's why we prefer a direct proof. Is it uses tools that have to do specifically with that problem. Contrapositive, you get a logically equivalent statement, and so you have proved it's true, but it's like a little bit like, we're going to look down our nose at the contrapositive proof, and like, I guess if we have to. Anyway, that was my quick rant, and that's all I've got for right now. See you all next time.